all these beautiful and expensive things. All are minerals, or have come from minerals. Just a few of an amazing array.
If you want to find mineral riches, rocks are the place to look. But you'll have to smash them open first. Have a look at what's on the inside.
Then you might want to polish them, because polishing really brings out the colours.
Or cut them into tiny slices and have a really close look. If you do, you'll see that rocks are complicated. They're really collections of tiny particles all stuck together.
These tiny, colourful particles are mineral crystals, pure bits of the stuff of planet Earth. Other examples are gold, because it's found as pure gold. Quartz is a mineral. It's a compound called silica. Diamond is a mineral. It's pure carbon. A mineral is a natural solid of uniform chemical composition, and that's what makes some minerals so beautiful. They can all make crystals. A crystal is a supermolecule. Its atoms are arranged into a geometric pattern that makes it much stronger than a random collection. This is diamond, the hardest substance known. Each atom of carbon links up to its neighbours in a neat pattern. A crystal grows when loose atoms are given time to gather in perfect order. It helps if they're free to move, that is, if the substance is a liquid or dissolved in a liquid. Here it's water. Then, as it turns solid, it may construct a crystal. Unfortunately, a perfect crystal only grows under perfect conditions. But in most rocks, minerals are in competition for space with other minerals, so their crystals are crammed together, and often so small that they can't be seen with the naked eye. There are thousands of minerals.
Let me show you some examples of the four most common groups of minerals. This is a mafic mineral. This is mica. This is feldspar. And this is quartz. Now, the size of their crystals doesn't matter. That's just more or less luck. But what does matter is that these four minerals, when mixed together, make up over 90% of the rocks found on the Earth's crust. Why? Because they contain the two most abundant elements found in the Earth's crust: oxygen and silicon.
What are oxygen and silicon? Oxygen with hydrogen becomes water. Oxygen in the atmosphere is a gas. And silicon? Silicon is a bright, flaky element called a metalloid. It's used in computer chips. But despite the fact that it's everywhere, you'll never find it pure like this. It has to be extracted.
Because it was all oxidized ages ago, and the result is silicate minerals in all directions. This is their basic building block, a silicon atom joined to 4 oxygen atoms. This unit can go together in many different ways, like a chain. Most mafic minerals are put together this way. They are mostly chain silicates. Or the silicate building blocks can go together to make a framework. The atoms in quartz are put together this way. Or put some aluminium atoms in place of the silicon atoms and you get a different framework. That's feldspar. Or build them into sheets and you get the flaky structure of mica. The point is, the properties of a mineral don't just come from the kinds of atoms in it, it's also in the way they're put together. Diamond versus graphite is perhaps the best known example because they're both made from carbon atoms, but you'd hardly think so because their properties are so different.
So rocks are complicated. Their minerals have many chemical compositions and structures. Yet because so much of Earth is just 4 versions of silicate, most rocks can be easily identified, and they have a common story. This is how all rock begins. Out of magma. The liquid rock underground. It begins hot and molten. This is a lava landscape. Rock frozen out like this is called igneous rock, which is the Latin for born of fire. Here the rock came out of a volcano, but many igneous rocks did not. Many cooled and solidified deep underground millions of years ago. Now, finally, they have emerged on the surface, maybe uplifted by great pressure or uncovered by erosion, or both. They are called plutons, a reference to their origin in the underworld. Sometimes magma pushing up has forced its way into cracks in existing solid rock to form intrusions. Here it's obvious that the dark rock was liquid while the light rock was solid. Pieces of it even cracked off with the force and drifted into the dark magma. Igneous rocks are all made of interlocking crystals, something that is easily seen under the microscope. In cooling, the mineral with the highest melting temperature formed the first crystals, which grew until the next mineral crystallized around them, and so on. This means they are tightly bound together, so igneous rocks are generally very hard.
Of course, when lava comes straight out of the volcano, it cools really quickly, so crystals don't get much time to form. This is a chunk of andesite. See? Tiny grains, very small crystals. This, on the other hand, is a chunk of diorite. Now, even though these two are made from exactly the same minerals, the crystals in this one are much larger. That's because it cooled much more slowly deep, deep underground. This is volcanic, but this is plutonic. Sometimes you can get very large crystals. Now, this comes from very slow cooling. Or you can get crystals from water being in the magma. This is called pegmatite. See? Very large crystals. As the minerals with the highest melting temperatures crystallize, they push the water aside, and finally, the remaining melted material becomes very rich in water. This helps the final crystals to become quite big. This separation process, brought on by slow cooling, can concentrate the rare minerals too, so pegmatite is worth looking for.
You might think that a rock is something that will last forever. But once they are exposed on the surface, all rocks are doomed. It's only a matter of time before weathering and erosion split, scrape, pulverise, dissolve and carry them off far and wide to become particles of regolith and soil. They are ground down into pebbles and sand, and down is the operative word, because sediments mostly come to rest in low places. It's underwater mostly, in lakes or under the sea, where they accumulate thickest, slowly compacting under their own weight, and with dissolved minerals acting like cement, the particles find themselves once again fused into rock. But this time the rock looks and feels quite different. These rocks were not born of fire. They were born of erosion, deposition, compaction and cementation. They are sedimentary rocks. The main feature of sedimentary rocks is bedding, the appearance of layers on layers. It's what you would expect from many years of slow build-up, interrupted from time to time, perhaps by droughts, perhaps changes in sea level, or different sediments arriving. Fossils in a rock are clear proof that it's sedimentary, and sometimes the whole rock is fossil. So it's in sedimentary rocks that we look for the history of life. Sedimentary rocks are the only kind made gently enough to preserve the remains of living things.
Sedimentary rocks range from this type of thing, called a conglomerate, where you can see pebbles of the original rock sticking out all over it, through to sandstone, where if you can scrape it, you can see it's made from tiny particles of sand all stuck together. Then we move along to shale, which is made from tiny particles of mud and clay. In fact, if you lick it, it even tastes a bit like mud. So that's the trick with sedimentary rocks. If you look at them closely, maybe scrape a bit off, or even lick them, you can usually tell what the particles are. So, sedimentary rocks are easy to tell apart from hard, crystalline, igneous rocks. But what would you make of this one? It has layers like a sedimentary rock, but crystals like an igneous rock. This is an example of a rock that's been tortured. I mean, if rocks could scream, this one would be going,
You have to use your imagination to guess at the incredible forces that push rocks up into mountains that can squash them into shapes like this, or the temperatures they feel if they're driven down near the mantle. We can get some idea by torturing rocks ourselves, but even powerful machines have trouble reproducing conditions deep in the Earth's crust. Of course, if the rock goes down far enough, it melts and its minerals may one day be reborn of fire. Still, many rocks survive the torture, although it changes them. Millions of years later, they may reappear at the surface in their metamorphosed or changed forms. So they are simply called metamorphic rocks because they have changed into something different.
Take a piece of limestone, which is a sedimentary rock. Increase the pressure and temperature for a long time and it turns into this, marble, a metamorphic rock. Or take another sedimentary rock, shale. Increase the pressure and temperature onto this and the minerals are actually pressed together and you get slate. If we increase the pressure and temperature even more, the minerals are actually separated and recrystallize into layers. This rock is called gneiss. If we go much beyond this, the rock actually starts to melt. This is migmatite. Parts of the rock have melted, but this one didn't go all the way. Migmatite is an example of a rock which has been partly melted. So, it's not metamorphic anymore, and it's not igneous. It's a bit of both. It shows how rocks are constantly crossing the boundaries between igneous, sedimentary, and metamorphic.
This is the rock cycle, from magma to igneous rock, worn down to sediment, lithified to sedimentary rock, maybe changed to metamorphic rock, which, if it's heated enough, returns to magma, and all the possible pathways and shortcuts in between. How many times has the rock that you pick up been changed? For 4.5 billion years, planet Earth has been cycling its rocks from one form to another. And it continues. Igneous rock is still being born. Weathering and erosion are still breaking rock down. Sediments still gather. And mountains are still being built. Humans have relied on the rocks for many things, from flint tools to clay for pots. Now, with a better understanding, the science of geology studies the rock cycle carefully because it can lead us to metals, gems, coal, oil and gas, the raw materials of power and technology.
Online teaching resources to support this program are available at abc.net.au/SchoolsTV.